Thank you very much. So I will start the show. Hello. Thank you all very much for coming. It's great to be here. So as Jorg said, my name's John Hardy, and I'm presenting work done here in collaboration with Christian Weichel, Faisal Taher, Jason Alexander, and John Vidler. This work is part of the GHOST project, which is a European collaboration of 4 universities looking at the future of shape-changing displays. So today I'll be talking about ShapeClip, which is a rapid prototyping tool to help the community really explore shape-changing displays more effectively. So what do we mean when we say shape-changing displays? So the definition we use is sort of self-actuating display services that change their physical geometry. And the first thing people tend to notice is they look kind of awesome. But more academically speaking, they expand the set of ways we can interact with computers. And they change the way, they expand the way we can design with computers as well. They leverage our inherent human physicality, because we're 3D beings living in a 3D world. And in that sense, they're kind of an emerging class of computer interface. And as with many other sort of emerging technologies that we're just starting to explore, we are facing a couple of immediate challenges. So the first of which is overcoming the high build complexity. So we needed an idea or system that makes shape change easier to build. And the second is engagement. So more engagement with shape change will help us understand why and how it's valuable as a community. So in other areas of HCI, we've got really well-established tools and which have sort of helped expand the breadth of applications that the community can produce. So I'm going to start by talking about complexity. So this is a merge. It's a 10 by 10 shape-changing bar chart that will be presented on Wednesday. Under the hood, there are a lot of moving parts. There's nests of wires, circuits, sub-millimeter tolerances, control systems, and then application software which drives it all. So we really needed to drastically simplify the process of building these things. Because even with the essential specialist skills and equipment, lots of iterations required, not to mention cost and a lot of patience. And this kind of led us to 2 design goals. The first of which is that shape displays should take hours rather than weeks to build. And this would enable lots more iteration, throwaway designs that can sort of keep time and cost low. And secondly, we wanted to engage a wider range of researchers and designers. So we said that programming shouldn't be a skill requirement in order to create motion designs for these things. So these 2 design goals led us to develop the ShapeClip. I've got one here, which you can come and have a look at later. And this is a modular linear actuator that turns any display surface into a shape-changing display surface. So this uses light emit by a screen to drive height and color. So let's see them in action. We're going to turn this screen into a shape-changing display. So first things first, we put down this grid and place 20 clips onto it in a 5x4 configuration. The timer at the bottom is counting down how long it takes. We plug them in, the clips auto-calibrate, then the screen will flood fill white in a second. There we go, and we're done. So I'm going to show you a couple more applications of this very quickly. We've got magic lenses, terrain maps, we've got graphs, we've got force-reactive interfaces, graphical equalizers, and sort of more gesture-based things. So let's look at how we do this with the shape clips. So an individual shape clip here is about 8 centimeters long when it's fully open, 2 centimeters wide, and costs just less than $15 US. So when you detach the removable arm and you slide off the 3D printed base, you see there's a stepper motor there, and that's the kind you find in old DVD drives, so they're quite cheap to get hold of. So we'll flip that over, and you can see there's an Atmega 328P processor, like you get in an Arduino, a stepper driver on the back, and 2 power connectors so you can chain them. We've got 2 LDRs at the base, and these sense light from the display. We've got 2 channels, one for height, one for color. And then an RGB LED at the top, which we can use to show color. So let's put it all back together and pop it on a display. So you can see there that the display's showing black, and it's closed. We show it to white, and it goes all the way up to the top. Black closes it down again, and white opens it up again. So it's quite a simple thing. Shades of grey give you sort of middle heights in between. So this is a very simple idea. People grasp it very quickly. It's inherently modular and scalable, and it lets us achieve our goals. We can throw these things on a display and create them in hours rather than weeks. We don't need programming. We transform our control of the pixel, which we all can do quite effectively, into control over shape. And the added advantage here is that these are quite low cost. So one of my favorite things about the ShapeClip is that users are free to work with whatever tools they sort of wake up in the morning and feel most familiar with. So motion designs can be created using well-known graphics packages. We've got a few here. We've got Paint, Illustrator, Photoshop. PowerPoint's quite an interesting one because you get interactivity through that. And these support non-programmers. And then for the programmers, we've got sort of a web-based graphic API, which is HTML5, CSS, JavaScript. These wrap sort of common advanced functionality, so we can send serial messages to them should we wish to. And also we can use the Arduino toolchain to reprogram the ShapeClips. So this dual approach to end-user development makes it very easy to test motion designs immediately without recompilation. We can enable clip operation across multiple devices. You can pick them up, put them on an iPad or a phone or a computer. And also we can very easily integrate rich graphics and multimedia into the designs. So the next challenge was engagement. So how can ShapeClip help the Kai community? So everything we've produced is open source. You can go to github.com/Lucy/ShapeClip to have a look at what we've done. Here you can find the board designs, the CAD models, the firmware, the application examples. They're all free for download. However, we do recognize that manufacturing hundreds and thousands of these things by hand is a big effort. If you're handy with a soldering iron, but you're not a fan of repetitive tasks, or you happen to be a grad student, like me, we've decided to go a step further and let you go to ShapeClip.com. And here, if we get enough interest, we plan to go and manufacture a bunch of these things at cost to really help people get started. We expect them to come in at around $15 a clip, but yeah. And we want to use this as an opportunity to really start building a support community who are experimenting with shape-changing displays. But before we could get to that stage, we wanted to first validate the design and make sure it was something useful. And we did this in 3 ways. Firstly, we wanted to make sure they worked together cohesively, that all the features worked and that there's a well-defined scope for these things. Secondly, we wanted to run a designer workshop to make sure that they were appropriate for the user community they were targeting, that they could pick up and construct their own ideas. And lastly, and this is kind of ongoing, we wanted to distribute the ShapeClip and reflect on the real-world usage of it. So to do the first one, we've got a number of features enabled by the ShapeClip. The first one is the portability aspect. So we've got here some ShapeClips, 25 of them placed on an iPad to show an interactive magazine graph, and you can see them picked up, turned around, shaped a little bit. And this is kind of interesting because you can start to pass them around a room and analyze data in an interesting way. We've got interactivity. Here, you can react to external input sources, so gesture, force, depth cameras. And within themselves, ShapeClips have a little wire that runs down them, which lets you forward capacitive touch events from the top down to a screen at the bottom. In terms of scale, this video shows the same application running with a single and multiple clip arrangements. So there's no artificial scale or resolution limitations of the ShapeClip beyond the size of the display surface and the number of clips you can pack onto it. In terms of density, we don't require a fixed density, so users can place and reconfigure the clips at will. It's only limited by, say, the number you can fit next to each other. Topology is a particularly interesting one because you can vary the topology of the clips at runtime. As you can see there, that bottom one is moving around and it's reflected in the simulation at the top. You don't need a known or fixed spatial relationship between the clips at the time you design your application. It's only limited by the line of sight of the control surface. And lastly, we have orientation. So clips can be reorientated locally to turn to face a user or globally as a whole display. And you can, say, rotate them upside down as well. So you can see the operation of the ShapeClip there quite clearly with the gradient. They are also hot swappable. So like all mechanical systems, the clips are subject to failure, and should a clip fail, you can easily replace it on the fly without even unplugging the power. Clips can be augmented with additional materials to change their appearance or colour, and you can add additional interactive capabilities like force sensors and things like that. And there are assemblies, so clips can be arranged to achieve specific objectives like tilting, stacking, pushing, pulling, or levering. And you can get special 3D printed bases for these which can achieve expanding volume, style, deformations, and things like that. So the next part of our evaluation invited 7 designers to a full-day workshop. The mean age of these people was around 30 years old, and all had formal training in their field. So we had graphic design, advertising, sound and multimedia, materials, cartography, and AV engineering. So we filled this room with technology like projectors, interactive tables, batteries for the ShapeClips, and monitors of various sizes. And we divided the day into 4 stages. So firstly, we threw around some paper airplanes and introduced the idea of shape change and the ShapeClip. Then we asked people to come up with a set of ideas that they could use it for. So we've got those on the window there, on the post-it notes. Then we asked them to go away and pick a few ideas that they really liked and actually build them with the ShapeClip to see if they could actually be used to create their designs. And lastly, we reflected on their feedback, asked people to put what they liked, disliked, improvements and thoughts. So overall, 86 ideas were generated, and of these, around 88% were deemed possible with the ShapeClip. 6 major ideas were built. So here we've got 2 sound equalizers at the top, A and B. The first one, A, was built by participant 3 and 7, and it took them around 2 hours in total. And the other one, B, was built by participant 2 in around 30 minutes. And the interesting thing between the 2 here is that one was built by people who knew a bit about programming, and they used processing to control the clips. And the other one was built by, that's B, was built by somebody who had no experience with programming at all and was able to adapt their logic software to produce the equalizer effect. F and G at the bottom are an interactive advertisement. So we all know the problem with display blindness. People tend to ignore public signage. And this designer, she wanted to try and address that problem by making a display jump out at you. And she, interestingly, didn't arrange the clips in a grid-like structure. She made them follow the lines of a design and used Lego to affix them all together. And that took her around 1.5 hours in total. We had a shy robot, which is picture E, and this was, the clips were turned upside down and then they would block natural light coming from it, and if you used your hands correctly you could sort of make it waddle across the desk. And at the top we've got C, which is this sort of dynamic graph visualization. Took them about 2 hours to build. It used 16 clips, and they took their existing knowledge of GIS software to render a grayscale height map, and then projected a Google map corresponding on top, and they could use the arrow keys to page through so you see the dips and the mountains appear. So overall, I mean, like many people up here, I'll say the overall reception to our workshop and our technology was positive. All participants agreed that they could understand the technology and they could work with it well, and they were all, interestingly, able to construct their ideas within the prototyping session. They used a wide array of tools to control the clips, including web browsers, Photoshop, processing, sound visualization software, and simply messing around with the natural light. And it was encouraging to see them combine with other technologies that we hadn't considered, like GIS. So no participants indicated that they could not satisfactorily control the clips. In terms of more reflective stuff, toward the end of the workshop, the clips started to get quite hot. I mean, they'd been running most of the day, and the heat and the noise generated by the motors the participants felt was too much. One clip was broken when it was plugged in upside down, which means we should probably use a one-way power connector. And interestingly, the modular nature of the ShapeClips meant that they were shared a lot between the session. People would go and ask for some from another, or take some out of their design and give them to somebody else. And people didn't treat them gently, right? So if you were running a user study with an iPad, people wouldn't throw it around the room. And they did with the ShapeClips, which maybe speaks to some affordance of their sort of structure. They'd like to see better support for attaching materials, like attaching Lego tops or Velcro, because most of the time was spent assembling the actual system rather than managing the ShapeClips and controlling them. So in context, really, in terms of their effectiveness as a prototyping tool, we're confident that they can support the sort of inventor and early adopter groups. And we observe similarities to other sort of foundational technologies like this trial and error approach to design, the reduced cost of failure, and quick runtime adjustments to designs. And I wanted to end by giving you a flavor of what's happening so far. So they've been used within our group to study force-reactive interfaces. We've had a mobile data physicalization which can be passed around. They've been used as a testbed for a shape display shader language, which will be presented as a poster tomorrow. And interestingly for me, as a boundary object to ideate about different applications and different values of shape-changing interfaces. And one of the participants in our workshop was interested in publishing it in a GIS context as well. There's another group looking at construction toolkits such as Lego. So I'll conclude by saying that thank you very much. ShapeClip can turn any display into a shape-changing display. This massively reduces the complexity of prototyping these things. And by exploring a greater range of designs, we hopefully let you, people with ideas and applications, engage with the benefits of shape change and evolve our understanding together as a community. So thank you very much. And if you're interested in getting hold of these, head to shapeclip.com and register your interest. Thank you very much.
Hi, Hiroshi from MIT Media. Thank you very much for the very, very exciting work. I like two things. One is you made a pin graspable on GUI. So this manipulability is great. Also, GUI provides very, very flexible platform, horizontal screen. And my question is, this is great to democratize these shape display, but to go beyond, there's so many conflicting parameters. For example, resolutions or speed, or translations, or sensitivity of touch. And which parameter you really think more important than others to go to certain direction? So we are exploring, but if you can share your thoughts about technical development direction, I really appreciate it.
That's a fascinating question. I'm not sure I have an answer, really. We find very much that it depends on who's using them and what they're building it for. So it's but generally, from what we've seen in our sort of technological context, it's the height and the ability to augment it with other things that's interesting.
Thank you.
Thank you. We hope that as a community we'll be able to sort of unpick these different challenges as we go forward. Any more?
So I think we do have time for another question. Maybe one question in between. What if you put a camera underneath? Do you think that would increase, that would work first, or would increase in expressiveness?
Yeah, absolutely. At the moment, we've got two LDRs at the bottom, and these are, they're not the best way of doing this. I think we've seen, since we've built it, a few better ways, one of which is putting a color-sensitive CCD there. And we hope that would increase the information bandwidth, so we wouldn't need to do clever ways of communicating with them. And we hope that people will take these, reprogram them, and show us how to do it better. Thank you.